And today we officially graduate from 1D, and we are moving up in the world to 2D. And we are going to start talking about equilibrium. And up to now, we did everything in 1D. So we only said some of the forces in the x direction must be 0. And we learned that in order for a deformable structure to be in equilibrium, not just the entire structure must be in equilibrium, and that's how we find our reactions, but also every part of the structure must be in equilibrium. So there are internal forces in the structure that keep the structure in equilibrium. So in 1D, everything is pretty nice, and just one equation to worry about. If we do the full 3D story, the full 3D story is a little more complicated. So if we have a body, a three-dimensional body in x, y, z space, on this body there is going to be forces in every which way, going in every direction. And on top of forces, there is going to be what we call concentrated moments. So did you see your little review of forces and moments? So concentrated moments is what you would have if I stick a screwdriver in this body right there. Boom. I stick a screwdriver and I twist the screwdriver. So really what I'm doing, I'm giving two forces, a force couple here. And by twisting the screwdriver, I apply a concentrated moment at this point D, where, let's call it MD, where the screwdriver is stuck. So this is what is called a concentrated moment. And what we typically draw for a concentrated moment, we draw the axis of the moment with a double arrow to remind ourselves this is not just a force, it's a concentrated moment. And you gotta follow your right-hand rule. So if I have the axis of my humongous screwdriver here like this, if I'm twisting like this, my thumb is going like that. So a moment that twists like that has an axis that goes with my thumb. Okay? So if I point the arrow that way, it means that this screwdriver is turning that way and giving me a concentrated moment at this point, MD, like that. So now I have a body in space, and it has got all these forces and concentrated moments on it. So for it to be in equilibrium, it's not just enough that the sum of the forces are 0. But like if I have two equal and opposite forces pulling on this, the thing moves. Because if I'm pulling left and right like this, the balance of forces in this direction is 0. But there is a net moment acting on it. So it rotates, right? So I have to be worried not just on balance of forces, but I also have to be worrying about the fact that the body does not rotate in space. So to make sure that it doesn't rotate in space, what I check is that the sum of all the moments acting on the body must be 0. So who's making the body rotate? Well, the forces make the body rotate, right? Because if I pull, and they kind of cause the body to rotate in different ways, and the concentrated moments make it rotate. So the way that you want to figure out if the body is in equilibrium is you choose a pivot point, Q. That's your pivot. You can choose the pivot inside the body. You can choose this outside the body. You choose the point that you want to use as pivot to make your calculation convenient. So you choose one pivot point, Q, and then you calculate the moment of every force acting on the body with respect to pivot point Q. So this is your cross product between the vector that goes from Q to P. Say, for instance, this is point P, the point of application of Fp. Then you do the vector from Q to P, that is RQP. And then you do the cross product between RQP and Fp. And this is the moment of force Fp with respect to pivot point Q. So you sum all these effects from all the forces, sum F1, F2, F3, sum them all. And then you also sum in all your concentrated moments. These concentrated moments sum in the sum of the moments with respect to pivot point Q independently of where the concentrated moments act. If I got a screwdriver here, what? It sums. Here, what? It sums. It doesn't matter where your pivot is. Concentrated moments always sum in your balance of moments. And this is from forces. you do this, and then you have to do your x, y, and z components of this equation, and each component must sum to 0. Each of the x, y, and z components must sum to 0 for the body to be in equilibrium. So as you see, it gets pretty involved, a lot of complex geometry. You have 6 equations, and things get pretty complicated quite quickly. So because we cannot go from 1D to 3D in one jump, we're going to go through easy steps through a 2D world. Yes?
When you're taking the force equations, you have to take in the moments into consideration for the forces too, like concentrated moments?
No. The concentrated moments do not sum in the sum of the forces. And the reason, it's a very good question. The reason that they do not sum is, remember, each concentrated moment is given by a force couple. So together, when you sum them up, they give you 0 in the force equation, right? That's why the concentrated moments do not poke their head in here, because each concentrated moment is made by me doing pull this way on one spot, pull this way on the other spot. The force times the arm gives me the concentrated moments that don't come into the sum of forces, okay? So this looks like a mess, and we're not going to go directly there. Yes?
The first term, the R cross F, so you have to do it for every single point that there's a force, right?
Every single point that there is a force. So if you have this force here, you do RQP, FP. There is another force here, you do this other R times this force, this other arm times this force, this other arm times this force. And you see each of these moments then is going to be orthogonal to the plane described, to the plane defined by the R and the force. They make a plane together, these two vectors. And the moment is going to be orthogonal to that plane. So in 3D, it gets pretty hairy. Let's take a break before we get there.
So it can be at equilibrium at one point, but not equilibrium at another point?
No, we're looking at the entire body. So we are looking at the whole body as a whole. We're not doing equilibrium at one point right now. We're just looking at a whole structure of body. Or this can be part of a structure, right? So I'm just doing this blob, this potato, sitting in space. But when I do a real example, for instance, I may have a beam like that. And on this beam, I may have forces acting on it. And I may have concentrated moments acting on it. Okay? So when I check if this thing is in equilibrium, I take it, and I choose my pivot, say I choose a pivot here, and then I do the sum of the moments of all the things that act on this body. And I see if when I sum them up, they sum to 0 overall over the whole structure. And if they sum to 0, it means this chunk that I've taken is in equilibrium. Okay? I'm not doing equilibrium of one point. I'm doing equilibrium of a whole potato, or a beam, or whatever, but a body.
So like that equation is only to find the moments for at point Q, though, right?
No, this equation tells me this is the moment of all the forces acting on the body with respect to point Q. Q is arbitrary, because if this is true with respect to a point Q, and the sum of the forces are 0, what is a very important thing is that if I choose another pivot, so if this is my pivot Q, you say, but what happens? What if instead of choosing this point, what is so special about this point Q? The answer is nothing is special with respect to this point Q. Because if you choose this Q, and she comes in and say, I hate your pivot point. I'm going to choose a totally different pivot point. I'm going to choose this pivot point here. I'm going to call it pivot point R. Okay? And I want to see if I'm in equilibrium with respect to pivot point R. She's going to do exactly the same thing, but she's going to be RP, FP, sum MD. And guess what? If you had 0 with respect to Q, and you have 0 sum of the forces, she will find that automatically the sum of the moment with respect to R is going to be 0. Because essentially, when you take a moment with respect to R, when you do the radius from this point to this point, you can imagine that it's made of going from here to here, and then from here to here. And then this part here, when you take it into account, is going to be always the same for every force. And you're going to end up with RQ, big R, cross sum of all the forces, which is 0. So I'm kind of going a little quick and skipping a lot of steps because right now this is not something I want you to worry too much about, this whole 3D thing. But the important take-home message for this is when you do the sum of the moment with respect to pivot point Q, you choose the Q. Once you put it in equilibrium with respect to moments, with respect to one pivot point, and once you made sure that all the sum of the forces are 0, once you're done these two things, it means that your body is in equilibrium with respect to any pivot point. I can take a pivot point in Watertown, and this thing is still going to be in equilibrium. Okay? Doesn't matter where I take my pivot point. Once it's in equilibrium with respect to one pivot. We good?
Yeah, thank you.
Excellent. Okay, let's do then the easy step towards 3D. So we're going to do equilibrium in 2D. Okay, so instead of being a potato, I just have like a pancake. Notice always food, potato and pancake. I swear I don't do it on purpose. It just poof, comes out of my mind, is food. It's like crazy. Okay, so in 2D, I got the pancake here, and I have a nice two-dimensional plane, X and Y. And then in 2D, I'm going to have forces. So 2D problem means the forces are in the XY plane. The structure is in the XY plane. So you may have like a force right here. This would be F1 if it is a point P1. And then you may have another force here, F2. Maybe this is point P2. And then maybe you have a concentrated moment here. Say this is a point D1. And this moment here is MD1. Now notice that the way I drew this moment, right? If I have the whole structure in the XY plane and all the forces are in the XY plane, the body essentially rotates in the XY plane. And the balance of moments I have to worry about is only the balance of moment that make me rotate in the XY plane. So if something rotates in this plane, which way is the axis of the moment? Which way does it point? To you. Out of the board. Right? So in 2D, I'm worried about the sum of the forces in the X direction, the sum of the forces in the Y direction. I want to make sure this thing doesn't move left and right, and I want to make sure it doesn't rotate around. So I'm worried about the sum of the moment in the Z direction. Okay? So only 3 equations, which is better than 6. Not as good as 1, like we had, but we can still handle it. So notice when I say sum of the moment Z, this means absolutely zilch up to when I give you a pivot point. You say sum of the moment Z what? Well, I need to tell you sum of the moment Z with respect to some pivot point Q. So you choose your pivot point Q, say that, I do not know. See, I can choose it inside the body or outside. Now I'm going to choose it outside, just for the heck of it. This is my pivot point Q. Say that I want to find what is the moment of the force F1 with respect to pivot point Q. You can do it 2 ways. You can do it, so how do you do the torque in your basic physics class? You look at the force, you look at the line of action, you look at the arm, and you can do arm times the force, right? And so you see that with respect to this pivot, so you always imagine you're sitting at the pivot. You imagine you're standing up right there at the pivot. And you're looking which way the force makes you rotate with respect to the pivot. So you see this force, see, it makes me rotate this way, right? So you see that this force is going to give me a moment Z with respect to this Q that comes out. So if this is X and this is Y, Z comes at you. So any moment that turning this way, what is the sign of its Cartesian Z component? Plus or minus? Brilliant. Plus. Okay, so this MD, you see that it's going to have a positive. This is a vector. And I show you which way it goes by giving you the direction of the curl of that vector, of the rotation of that vector. If it does that, it means this comes out at you. This is going to have a positive z moment. If I have something that looks like that, it's going to have a positive or a negative z moment, this guy. Negative, fantastic. Now, to do the moment of the forces, to sum up into that equation, one way is to just figure out, the force, the arm, and like that. If it gets complicated, I like it when you use just Cartesian component of things, because you split things up and life gets so much easier. So instead of writing, so I can write the moment z with respect to point Q is going to be equal to the sum of all the z component of the concentrated moments. Wherever they are, they sum in. This is going to be plus, this is going to be minus, because I'm summing into the z direction. Plus, I'm going to sum all the R, Q, P cross F at P. So this is the vectorial thing, so the z component of this. Instead of writing it like this, in Cartesian components, you can split, so the RQP is the vector from Q to P. So you can do so this is the R. This vector here is RQP. You can split it in two parts. You can split it in the horizontal component, which is this guy, and the vertical component. So this is Rx of QP, and this is Ry. Ry of QP. So you do Rx and Ry, and the same thing with the force. Let me get rid of this moment because it's in the way. So if I look at that force, I can also split the force in the Fx and the Fy. See? So if I do it that way, my cross product, you can see that Fy only acts through Rx and makes me rotate positive. So this is going to be Rx QP Fyp, and Ry only acts through Fx, and you see that a positive Fx and a positive Ry makes me rotate negative. So I have minus Ry QP Fxp. So this is the z component of that thing. When I sum all of this with respect to the same pivot point Q, I have to get 0. So when I do equilibrium in 2D, I'm worrying about summing the forces in X, summing the forces in Y, summing the moment in Z. And when you sum the moment in Z, you can take your shortcut, force times arm, or you can do it Cartesian like I did. Okay? This kind of knowledge, we're going to use it a lot when we do beam bending. Now, we're going to do a little trick of kind of easing our way into beam bending by getting ready along the way. So for now, kind of store it in the back of your brain. We're going to use some of these concepts. One thing that we did not discuss yet is this. I just drew the forces, the loading on it. How about reactions? How about supports? What's going on with the supports, right? So I hope you picked up this little handy-dandy handout. Of course, I see they're still here, so probably some of you didn't. Do you have it? Handy-dandy handout, come get it. So can you pass it along to anybody else? Okay, so supports. Up to now, the only kind of support, this is another of my very high-tech demos that we're going to do today. Okay, so up to now, the only support that we looked at is the wall, because, so this is the wall, which is also called a fixed support. The kind of structures that we do in 201 are like long, skinny structures, like this guy. So if I take a structure like this and I stick it into the wall, right? So that is stuck at the wall over here, like that. Right there, the wall is preventing any movement from happening, right? So because I have the wall there, the wall prevents this point here from moving anyway. So the wall prevents any x or y displacement. You see, it doesn't make it move. It's stuck in the wall. I'm holding it. The wall also prevents any rotation right here at the wall. If you imagine that you stuck this into the wall, this thing is not moving, it's not rotating. It's not just not translating. It's also not rotating. You see that? So it prevents any rotation along the z-axis. How does it do this? Well, whatever forces I'm applying to this thing, the wall is balancing them out. So in order to balance them out, it must provide a reaction in the x direction. It must provide a reaction in the y direction. And it must also provide something to prevent things from rotating. So see, the way that it would prevent this from rotating is pulling down here and pushing up here, right? So push on this side and pull on this side means that it's applying a concentrated moment to prevent rotation. Do you see? It provides a moment this way that if I try to push this down, the wall is like grabbing onto it and giving a moment to fight that, right? So prevents translation in x, translation in y, rotation in z, and gives reaction in x, reaction in y, and concentrated moment in z to keep things from flying away or spinning around. So this is our wall. You see? For every movement that it prevents, it needs to do something to prevent it. It cannot just say, I'm the wall. I give you the law of not moving in x. I give you the law you're not moving in y. It's got to put some effort into it. So it's got to give you a reaction, x, y, and moment. That's one kind of supports we have. Another support that we have, also demonstrated with the same fantastic high-tech thing over here, is called a pin. So if this is a pin is something that is sitting there attached to the ground, and the structure is attached to the pin through something like a hole, so that the pin prevents the structure from moving x or y. See, this end is not moving, but it cannot prevent the structure from rotating. You see? So a pin, also called a hinge, does something like this. We show it like that. So that's my pin right here, attached to the ground. I'm the ground. And the structure attached to the pin, like that. Here, the pin gives you forces so that this thing cannot go anywhere. So it prevents ux and uy. Notice that it prevents uy at the point where the bar is attached to the pin, so at point A. It does not prevent ux and uy of every other point of the bar. Notice that when I say the support prevents ux and uy, it prevents ux of uy if this is section A of the one that is, or the section that's stuck to the wall. We already know that even if this point is stuck, every other point can move in x, right? That's what we have been doing, calculating ux of x, right? So the wall prevents everything at the wall. The pin prevents displacement at the pin. So the ux at A and uy at A are fixed. So these guys, preventing them means they are 0, right? So it tells you how much is the displacement at the wall. 0. How much is the displacement at the pin? 0. If the pins want to dictate the fact that this thing cannot move, it's got to do something about it. So the pin provides Rx and Ry. The pin does not provide moments, so it cannot say anything about rotations. The bar is free to rotate. There is a duality between what you, oh my gosh, I'm like so strong. Yeah. Go ahead.
Doesn't for the wall, are we saying that there might be elongation? Is that why it doesn't prevent displacement for the whole entire?
Yeah, there may be deformation of the bar. That's why it cannot prevent everything. This thing can do that if it wants. If I pull on it, this is what we're going to learn for beam bending. This thing can rotate. Can rotate up, can rotate down, can do anything it wants, can get longer, right? But this section here cannot do anything, okay? The same thing for this bar. As far as this pin is concerned, the pin, maybe the bar started off like this. It can become like that once it's deformed. It can elongate. It can rotate, but it cannot move from this spot. Okay? So in order to do that, the pin must give Rx and Ry. And the last kind of thing that we worry about in terms of supports that we model are what is called rollers. And essentially, rollers are hinges on roller blades, right? I take a hinge, and the hinge is like, oh, I'm so happy I'm attached to the wall. And you say, no, you got to be on rollers. I put it on a roller skate. And so things that are, so now this one here, woo, can go left and right. See, nobody stops it from going left and right. Even if I draw it just with these little wheels underneath, doesn't mean it can fly up. It's still stuck to move along the sliding direction. So, for instance, if this was the x direction, notice that I can draw it this way. I may have a roller that is shaped like that. Doesn't mean that always needs to be in the x direction. I can have a roller like that. Woo! Okay? So what the roller does is it can only prevent this point of the structure from moving orthogonal to the plane of the roller. Okay? So in this way, the way I drew it with the x-axis, it prevents only uy, essentially prevents normal to the sliding direction. And in order to do that, needs to provide Ry. All these things are provided on the bar at the point of application of the reaction. Okay? You see the duality? This guy stops x, y, and z, must provide x, y, and z. This guy stops x and y, must provide x and y. This guy stops only y, must provide Ry. Okay? So these are the kind of reactions and supports that we're going to deal with in our 2D world. Okay? So these things, if you had supports and walls in a body, they sum up in your equilibrium equation, the same way as RXA is summed up in our sum over effects. Okay? We're going to do examples. I don't think that, okay, now you know everything, goodbye. So we're going to do more. But that's the basic concepts. One thing that I should say is that we cheat a little bit in 201 about this two-dimensional world, because another kind of problems that we do in 201 is torsion around the x-axis. So another kind of problems that we do is we stick something like here, and then, oh, my props are killing me. I stick something like this, and then I rotate. See what I'm doing? look which way is the axis of my torque. You see? Along this axis here. So the axis of the torque is in the xy plane. But the forces, see the way I do the forces, I need to point at you or point into the world in terms of, into the wall in terms of forces to make this rotate. So strictly, this is not an xy problem because I do moment with respect to what axis? This is the x-axis. For torsion, I'm doing moments in the x direction. But because I can draw them in the xy plane, because the axis of torsion is also in the xy plane, they're easy to draw and easy to deal with, so we're also going to do torsion along the x-axis. Okay? And for torsion in the x-axis, that means that the wall is going to prevent the rotation around the x-axis, and the wall can also provide moment along the x-axis. Okay? So that's not strictly 2D, right? But we can draw it into this, or we can do it. Okay?